The thing is, even if you have the lens, then you have to feed them basically. So we also looked at array feeding, that we made array so that different elements of the array would be fed, and depending upon how which element you feed, the beam can be sent into different directions, and then we measured that. This is here in my lab. So uh, what we have here is that we simulated and we measured the lens, and these are simulated as well as the measured gain values that we get. We are quite close. Now another type of circuit type of beam forming network is like a Butler matrix and Nolan matrix. Other matrix are also there. In here, I would just give a brief introduction to Butler matrix. So what we had in Rotman lens is that we had our own structure, and depending upon where we were feeding it, we were getting the beam in different direction. Here also in Butler matrix, it is similar to that. That you feed. So this is a matrix on the right side, maybe something like this. Okay. So you had different number of input ports. Then you have the different number of output ports. Depending upon which port you would feed, you can send the beam in different directions. So here we are showing, like, if you feed a particular port, the beam would be in one direction. If you feed another port, it would go into another. Depending upon which port you are feeding, then the beam would be getting steered into different direction. So it's again like you can change the direction of the beam depending upon which input port is activated. And this is the typical design. And now why we are talking about this? This is also one of the beamforming network, and we also saw like we were asking the community that should we have a basically should we work on something like this, where if you see it has hybrid coupler, phase shifters, crossover, and design like this becomes really complex. Like it would be something like this, a lot of transmission line and a lot of work. Like once you design it, and if you have changed frequency or any specification, it would be again difficult. You have to design it again. So we thought, okay, why not to basically make a software on that? And currently we are working on it. So Butler matrix, another beamforming network, and currently we are working on it so that once the software is ready, we would just click on something like we have for Rotman lens. You give the specification, it would automatically make the whole design for you. So it's more like a combination of computer science, electromagnetics, where because these are, if you look at it, see, if you have to understand it, these are just transmission lines, right? But the thing is that normally when we make in softwares like HFSS or CST or another software console also, then it's quite difficult. But once we tackle it with software, like automated, then we have to just click on something and the whole design would be made. So currently we are looking at it. Basically, some students are working on it. So like here we are showing it is 2D design, like only in one surface. Again, the beam can be sent into 3D direction also. Like in this direction, we can send the beam in any way. So then we can also basically complicate the Butler matrix, something like this, where we have 3D Butler matrix, and if you want to make it by any simulator, it would be very difficult. So what we are thinking is that this type of design, once we make it in a plane, then we would make into 3D also. So we still have some time. I thought that after this, so these are the beamforming networks currently we are working on. Rotman lens we already have the design that is pretty good, and we are still looking at some bugs that we are fixing, and we are also moving it from Python, because in the starting we were learning, so we are moving it from Python to C++ now. Then we are also looking at the Butler matrix. That is also a potential beamforming network, and we are basically making a software on that. One of the issue with beamforming network is that if you see it's quite big, and if it is big, then the material, depending upon which type of material you take, it can be lossy. So it has its own disadvantage, but still a lot of people use it. Rotman lens is also used. good thing with buttermetric is comparatively easy to design as compared to rod mill lens. But depending upon the size, it can be a little bit expensive loss wise. So we are still investigating it further. In coming months, I think we would have the software ready. Then we can again share with the community that where we stand. So currently we are working on it. Now regarding, I thought, okay, I would introduce our lab also, like where we are. So my lab is called Xiangshan lab, and we are closer to, basically this area is called Zhongshan, and we are like in India we have different states. So here we have province. So we are in Guangdong province, and we are closer to Hong Kong. So Hong Kong and Macau. So we are like 1.5 hour drive from Hong Kong and Macau. So regarding the different type of instruments, we go up to 750 gigahertz. And currently, we anechoic chambers and all that, we have the measurement capability up to 330 or mainly 300 gigahertz. We can measure up to 300 gigahertz. So I thought I would show some of the pictures that we have. So this is here, basically from one side of the lab. These are some of the designs that were made with the lab, as well as we also work with the industry. So they design with us. We have one far field chamber. We also have near field chamber. We have two near field chambers. So in here at the back, if you see, we have near field chamber, and we have uh, all the in all the chambers, antenna mounting we do it with robotic arms. So we have robotic arms that stand behind the antenna, so that we have much better control on the direction in which we want to basically orient the antenna. This is inside our chamber. So typically this near field chamber is something like this, that you have the radiating element, then so that we have the absorber on the other side. Then we have the robotic arm here, and we can move the direction. Basically, near field, you measure the field near to the antenna, and then from near field to far field transformation, you can calculate how the far field is. So we have two anechoic near field chambers. We also do antenna on chip, antenna in package measurement, and this is the closer view to the robotic arm, that we go close to antenna, and we can do near field measurement like planar measurement. We can also do cylindrical as well as spherical measurement, because it's a robotic arm, so you can just orient it anyway. This is another view of the field. And so because this is an international lab, it's not like a typical country specific lab, like it's there in the country, but it's more like an international lab where we want to collaborate with other people. We want to work with them. We also want to use their skill, and they can also use our skill, as well as we can collaborate with them if they need anything. So what I can say is a very very good lab resource wise. So if anybody wants to collaborate with us, we are ready for that. And two other companies that work with us. One another good thing about this lab is that in the campus we have another two companies that work with us. One company is Fragrant Mountain Microwave. So they make anechoic chamber as well as the measurement systems. So inside the campus, I haven't seen any facility like that in anywhere else, where you have the company inside the campus and they work with the lab. So it's like I open the door from they are on the other side of the lab. So basically, just adjacent to lab, I open the door and I enter into their company. So if we need any help, they are always there to support us. Because we have seen sometimes what happens, that the university are able to buy the equipment, but then maintenance is not so easy. So good thing with working with the industry is, like, if we face any problem, they can help us. So they make their own anechoic chambers, they make their measurement tools, and we also help them. Like currently, in here I have 3 students, 1 PhD and 2 master students. One of the master students is like working with robotic arms and looking at how the near field calculation is performed. Basically, we are researching on one of the topic. So one of the students like working on the anechoic, working on the robotics as well as interaction with the near field measurement. Another company that works with us, it it is their different office, but the main idea is that they make substrate. So it's like we have the measurement tools from one company, another company inside the campus. It's important to know it's inside the campus that makes, basically we have the a sort of factory inside the campus that makes the substrate also. They make very low loss substrate. It's like they have basically epsilon r of different epsilon r. They here I am showing around 2.5. But important thing to know here is their tan delta is very low. It's quite low to the market's commercial substrate. So we have a very good facilities in that way that we have our own material. We already have measurement tools in our lab. Plus, we also have a company that supports us. I don't I don't know if there is any facility like that in the whole world where you have make your own substrate and where you make your own measurement tools. And just to before finishing up, that these are some of the collaborators that work with me, and this main work that Dortmund Lens design, it came from these students. I forgot to add some more students that are currently working with me. So apart from NIT Delhi, some work is coming from JNU. I forgot to add their name. Maybe in next slides I would add that. And then there is also another university that is working with me, ABESEC, and all the contribution is coming from those universities now. So NIT Delhi, JNU, and another college. So other references that we use. And thank you everyone. Any questions?
Thank you very much, sir, for such an informative and wonderful presentation on beam farming and Rotman lenses design procedure in software. It is also very appreciable and remarkable. You have made a simulation software.
Yes, yes.
And yes, sir.
Yes.
And